Hello, welcome to the lectures on polymers. In this lecture, we are going to look at microstructure in polymers. Through this course on polymers, in which we have looked at the concepts related to polymers, we are looking at the properties, we are looking at several interesting applications, and of course, we are also discussing the overall sustainability aspects. In this week, we will start looking at the properties of polymers. In the first couple of lectures, though, we still have to look at the polymeric materials of different kind, and we will finish our analysis and understanding of the blends and composites. And so the focus in this lecture will be on learning concepts related to what is meant by microstructure in polymers. And specifically, we will also see some mechanisms of microstructure formation. So we will look at what are different microstructures, and then we will survey quickly the mechanisms which are of interest when we talk about microstructure. So polymeric materials, what is the different set of microstructure or structures at the microscopic scale that are of interest? And so if we look at, let's say, just the amorphous or glassy polymer, then the chain orientation is what is of interest. So, for example, if the molecules are oriented towards one direction, and we saw this, that orientation is a very important aspect related to applications of polymeric films. Similarly, if we have a semi-crystalline polymer, then the crystal morphology and orientation of crystals is important. So, the dimensions of crystal, we saw that the polymer chain folds itself, and this fold leads to formation of what's called a lamella. And so what are the dimensions of this lamella? And more importantly, how is this lamella distributed in itself, like we saw in case of a spherulite? So what's the spherulitic size, for example? So these are all aspects related to morphology of crystallization. Over and above, if there is an orientation associated with, in the case of spherulite, basically the ribbon-like lamella are distributed completely isotropically throughout the sample. But if we plastically deform this sample, then all the lamellas may get stacked on each other, and then there is a preferred orientation. So orientation not just of the chain itself, we may have orientation of the crystal lamella also. So both of these orientations are important from a microstructure point of view. And one of the things that you can immediately notice is this lamella will have an anisotropic property. If you look at in this direction, there is covalent bonds. But in these directions, basically there is only the polymer chains which are stacked with each other, and there is only energy of interaction, which is secondary interactions. And so the spacing also, the lattice dimensions, as we have seen earlier, A, B and C, will be different. And so that again indicates that crystal is an anisotropic entity, which has consequences both for mechanical properties, diffusion, and all the other performances. So therefore, orientation of these lamella will definitely determine what the overall performance is. Now, if we mix the two polymers, as we saw in case of polymer blends, and we have partial miscibility or immiscibility, then what is the sizes of the A-rich or A-lean phase? Or if it's A and B completely immiscible, then what are the domains and shapes of A and B? Similarly, in case of a copolymer, especially when it's a block copolymer or a graft copolymer, then again, what are the domain sizes and shape? And this we have repeated several times, that a polymer blend and a block copolymer or a graft copolymer have certain behavior which is similar, because we have basically segments of A and B. In one case, they are reacted with each other as a block copolymer, but in other case, they are free. But in terms of molecular level picture, both of these have some similarities. In case of a composite, when we add either a particle or a fiber or a fabric, then basically the distribution and orientation of fibers is important. If it's a spherical particle, then of course only distribution is important, because it's a spherically symmetric filler. But in case of fibrous or any other disc-like, any object which itself is anisotropic, we will need to look at the orientation in the final polymer composite part. So you can see that there is a wide ranging variety from molecule level to particle level that we have to look at when we discuss microstructure of polymeric systems. And in this question, for example, morphology, which is what we mean by microstructure, can be looked at using microscopy. There are several types of microscopies. We can look at optically using optical microscope. We can have a scanning electron microscope. So there is atomic force microscopy. So all of these are ways to look at what is the distribution on surface, or in case of transmission electron microscopy, since we use a very thin sample, we can look at the overall sample itself, and we can know what is the distribution of different components. So we know basically the morphology of the sample. And clearly then other techniques are useful for determining other parts of the structure of a polymeric system or its behavior. So one of the things that are important when we look at crystal melt transition to a solid phase, because in case of a semi-crystalline polymer, we are going from a molten state which is completely random to a semi-crystalline state where we will have a distribution of glassy and crystalline states. Or in case of a blend, where we look at the two domains of the blend, it is of interest to know what is the distribution of these crystalline amorphous regions or A-rich, A-lean phase. Those of you who are familiar with phase equilibria and have looked at, let's say, vapor-liquid equilibria or liquid-liquid equilibria may not have come across this. And can you guess why is the reason that in case of vapor-liquid equilibria, we don't really look at these phase separation mechanisms in as much detail? If you think in terms of vapor structure or in terms of liquid structure, the phase separation mechanism is not as relevant, because in the end the phase separated structure is identical, because there is sufficient molecular flexibility, mobility for the phase separation mechanism to remain relevant for the final properties. But in case of polymers, we are going to be in the final state, which is a glassy state, and therefore whatever phase separation mechanism can do to the distribution of macromolecules, it will get frozen there. And so it depends a lot on how the phase separation was done. And given that macromolecules are also very slow in terms of their response, and given that they are entangled with respect to each other, more often than not, it's the kinetics of phase separation which determines the overall phase separation boundaries or the domains. And so therefore phase separation is very crucial for polymeric systems, because it completely determines the microstructure in the final performing part. And so depending on the conditions of phase separation, the mechanism can differ. The mechanism generally depends on the second derivative. Again, because this determines the stability of the system, as we saw in the 29th lecture, where depending on the curvature of the delta G curve with respect to composition, we have stability, metastability and instability. And so the basic picture that we have of why the mechanism differs is based on what happens in a situation where there is a thermodynamic driving force for phase separation. But just because the thermodynamic driving force is there, it doesn't mean that phase separation will always happen according to same mechanism. It also depends on what is the level of fluctuations and how the different driving force, such as thermal energy, the interface whenever we create A-rich, A-lean phase or a crystal amorphous phase, what is the energy associated with that. So all of these determine what is the mechanism. So we've already seen in the 29th lecture that a temperature composition diagram can be used to describe different regions. And in terms of the second derivative of Gibbs free energy, so this is what will determine what is the mechanism in terms of phase separation. And what we saw was that if I take a blend which is in this condition, and if we maintain the temperature, then it's completely miscible all the time, no matter what is the composition. But if I cool the blend, then there is a possibility of doing phase separation by spinodal decomposition, or if I cool it slowly, then the phase separation may happen through nucleation and growth. So generally phase diagrams will also tell us about the mechanisms of the phase separation. And in case of macromolecules, there is a kinetics aspects involved also, because it may not be always feasible to cool or quench extremely rapidly so that we reach spinodal decomposition. Nucleation and growth may already set in based on the cooling rate that we see. And most often, because of this nucleation and growth being the phenomena which is immediately started, many of the practical systems we see nucleation and growth as the dominant feature. So let's look at that a little bit closely. The idea is that everywhere there are thermal fluctuations, and because of which the molecules are randomly changing conformations. Since there is a thermodynamic driving force for either crystal formation or phase separation, locally polymer chains are organizing themselves so that a rich region is formed or a crystal is formed. However, as soon as these regions are formed, we create an interface. And since we create an interface, there is an interfacial energy which is proportional to the area, 4 pi r squared. Let's say, so if we have a domain of this kind with a size r, and this domain could be either a crystal or let's say a rich region, then the interfacial energy associated with this is given by this, which is the interfacial energy, which is proportional to the area. And then of course there is a thermodynamic driving force which is related to the Gibbs free energy change, and it's related to the size, the volume of this particular a rich region or a crystal. So the overall Gibbs free energy is sum of these. So there is a driving force to form the crystal, but there is a interfacial energy term which is making sure that the crystal will melt again. And so this dynamic process keeps on happening everywhere. If we are above the melt temperature, then basically this term itself is not conducive. There is no thermodynamic driving force, and therefore no crystal is formed. Only when the sample is brought below the melting temperature or below the critical solution temperature, LCST or UCST or whichever are the critical transition temperatures, then only if the thermodynamic driving force is there, we will have a driving force for having the phase separation or crystallization. So therefore, because of this, the overall change in energy is positive, and it in fact also increases with R. So if you look at this delta G as a function of R, you can put some numbers here for delta G and gamma Cm, and you can see that this is how the variation will be as you change with respect to R. So in initial region, what happens is, in fact, delta G overall increases if the crystal starts growing or a rich region starts growing. So as soon as due to thermal fluctuation somewhere a small crystal or a rich region is formed, there is a tendency for this to again melt back, because that's how the delta G is lowered. But if you go in this region, then you see that delta G will spontaneously decrease. So there is a critical size of this crystal or A-rich region required, and that's what we call a nucleus. Only when it goes beyond this crystal size, our description says that okay, a nucleus has formed and now growth can happen. And that's why the two different stages, that there has to be a nuclei formed. There is a tendency of crystallization everywhere, or there is a tendency of forming A-rich phase everywhere, but certain places only nuclei formed because of this competition between Gibbs free energy change, which is the driving force for the crystal or A-rich formation, and then the interfacial energy. Of course, with time, our understanding of nucleation and growth has become much better, but for our course purposes, this gives us a basic idea as to why there is a certain set of places where nucleation forms, and then the growth can occur simultaneously. And so this barrier height to nucleation can also be estimated mathematically by just finding a maximum of this delta G, and it depends on the surface energy and the overall driving force. And nucleation therefore is dependent on what is this barrier energy. If thermal energy is more in terms of the difference between the transition temperature and wherever you are, then there will be a higher degree of nucleation. The other phase separation mechanism of spinodal decomposition, as I mentioned, is less prevalent, and it leads to generally co-continuous. Because there is a unstable phase separation formation, what happens is there is co-continuously everywhere A-rich region and A-lean region will be there, or polymer crystals will be spread throughout, and it's observed only in either lab conditions or for very few specific systems. So generally we will, one of the things that we have to be very cautious about is how is the processing being done on polymeric system affecting its microstructure. Because in the final part, it's the microstructure which is very important, but the processing will have a large influence on it. And during processing, we basically will make the polymeric material flow into a mold, or we will press it between rollers, or we will stretch it using a spinning machine. So all of these are operations in which we deform and make the material flow. And so is there any flow induced or influenced structure? For example, chains will orient in the flow direction. Crystals can also orient in the flow direction. Phase separation, the domains may also, so if we have a domain of A-rich region, which is largely this, if we create it under what's called a quiescent condition. Quiescent condition implies no flow or stationary phase. And so in this case, we may observe spherical domains, but if we have now a flow, then the domains may get elongated like this. So therefore, chain orientation or crystals or the domains of blends will get affected based on the processing conditions. And the shear rates which are involved, the stresses which are involved will significantly influence what is the microstructure that we get in the end. And in fact, this is a very important tool available to us to manipulate the microstructure of polymeric systems so that we get the desired performance. The other interesting thing about many of these macromolecular structure is depending on the chains or the crystals or the domains, if they respond to other fields, then we can in fact achieve microstructure by applying electric or magnetic field. So for example, electrospinning is a method of making fibers using an electrical field also. So when we apply electric fields, and if macromolecules have charges, then they will respond very differently to it compared to some other macromolecules which have less dipoles and less charges on them. So therefore, field assisted microstructure manipulation is also important in many of these applications. So in a nutshell, microstructure is very important because final polymeric part will basically perform according to the microstructure that's present. And this is what we had mentioned when we talked about processing structure property. So in case of polymeric materials, the three are interwoven with each other very intricately. And when we want to understand the behavior of polymers, we have to look at all these three aspects. And so morphology, of course, we have seen that microscopy is used, and in transmission electron microscope we can get results up to few nanometers. And then we will see also that like mechanical spectroscopy with rheology or dynamic mechanical analysis, dielectric spectroscopy, we have molecular spectroscopy where vibration stretching of covalent bonds tells us about which are the functional groups present. So one can identify quickly whether this is a polypropylene or whether this is a polyethylene terephthalate or it's a polystyrene sulfonate by looking at the groups which are present. Weight change with temperature is a very good way of estimating the thermal stability of the system. Of course, it's only aggregate or gross measurement, because even without weight change, certain reactions can take place, and therefore degradation can set in earlier than what is indicated by TGA. But from a gross measurement point of view, it's a very important technique. And we will have a lot more to talk about differential scanning calorimetry, especially when we look at glass transition, crystallization, polymerization. So many transitions that happen have thermal signatures. And so all of these techniques are extremely useful in determining the polymeric properties as well as polymeric microstructures. So with this, we will close this lecture. Thank you.